тебе.
Здравствуйте, сказала без звука включенного.
Тогда все, трансляция началась, я свое там лицо увидел, вот звук я у себя отключил в браузере, чтобы нам не мешало это. Вот, ну, в общем-то, все, 10 часов уже, да, давайте начинать. Let me tell some words. My name is Gerasim Krivovichev, and I am a moderator of this session. Today we have 3 presentations. All presentations must be made in English. Please, not more than 12 minutes are given for every presentation. Before 2 minutes of the end of this time, I will inform you about it. 3 minutes are given for the question. During the presentation, the audience will be muted. After the presentation, you can unmute yourself and ask the question. Additionally, the questions can be asked in chat, in Zoom or in YouTube. Теперь по-русски не нужно дальше то же самое сказать, согласно нашей инструкции. Да, меня зовут Герасим Кривовичев, я являюсь модератором этой сессии, ну и вот одновременно так получилось, что председателем. Доклады нужно делать на английском языке. Значит, на доклад выделяется не больше 12 минут, причем за 2 минуты до конца я вот вам об этом должен сообщить. Значит, дальше вопросы, да, 3 минуты выделяется на вопросы, то есть вопросы можно задавать, вот включив у себя микрофон, то есть в принципе во время доклада я должен все микрофоны отключить, кроме микрофона докладчика, соответственно. Вот, 3 минуты на вопросы, то есть можно задать вопрос, включив микрофон, либо задавать вопросы в чате. Есть чат в Zoom, есть чат в YouTube, соответственно. Мы транслируемся в YouTube. Вот, все. Let's start. And our first speaker our first presentation is detection of the community-acquired pneumonia factors leading to death. And the speaker is?
It's me. Yes. Good morning. My name is Alexandra Ajani. Just a minute. Can you see?
Yes.
And now? Okay. I'm going to present you our work, which is devoted to detection of the community-acquired pneumonia factors leading to death. My co-authors are Anastasia Goncharova, Daria Vinokurova, and Evgeny Kulikov. Community-acquired pneumonia is one of the leading causes of death worldwide. According to the World Health Organization, lower respiratory tract infections occupy the fourth highest mortality rate in the world. The Ministry of Health of the Russian Federation updates the clinical guidelines for the diagnosis and treatment of community-acquired pneumonia every 3 years. Prediction of the risk of death in community-acquired pneumonia is becoming increasingly important because this determines the choice of treatment site, the amount of diagnostic and treatment procedures. In this regard, the task of predicting the outcome of the disease based on the available patient data is relevant. It's noteworthy that pneumonia is a rapidly progressing disease that can lead to a life-threatening condition in a short time. Therefore, when a patient is admitted to the hospital, it's necessary to correctly assess their condition and determine the necessity of hospitalization. If the condition is incorrectly assessed, the patient may die in a few hours. There are special scales for patients with community-acquired pneumonia that help to categorize patients into different risk groups based on mortality. Different scales have their advantages and disadvantages because they were developed in different socio-economic and geographical conditions. Thus, none of them are generally accepted in the world. In Russia, assessment of the prognosis of community-acquired pneumonia for all patients is recommended to be performed by using the CARP-65 scale, according to the clinical guidelines of the Health Ministry of Russian Federation. The CARP-65 scale was developed in 2002 at the University of Nottingham in the United Kingdom. The creators of the scale studied 1068 patients, and this scale includes simple clinical and biochemical parameters which can be measured promptly after the patient is admitted to the hospital. There are some researches that confirm the effectiveness of the scale. However, some authors show that the CARP-65 scale should be used cautiously because there are patients who were classified as mild according to the scale, but later they died. So our investigation purpose was to detect the factors leading to the deaths of patients classified as mild on the CARP-65 scale. Lethality of community-acquired pneumonia was studied based on the data of all patients hospitalized with community-acquired pneumonia in all hospitals in the Tomsk region in 2017. The database contained information about 1412 patients. For each patient, 2050 indicators were requested, such as age, gender, social, clinical, laboratory, and radiological characteristics. We considered the patient's death as a predicted variable. The CARP-65 scale includes an analysis of 5 signs: impaired consciousness due to pneumonia, an increase in the level of urea nitrogen, respiration rate, a decrease in systolic and diastolic pressure, and the last one is patient age. The presence of each symptom is valued at 1 point. The total amount of points can vary from 0 to 5, and the risk of death increases with increasing amount of points. For each patient, a CARP-65 scale factor was calculated. Of all patients, the following groups were identified based on lethality and CARP-65 score. The first group is patients with light onset who later died. This group consists of 20 patients with total score 0 or 1, and this group is of interest because these patients were classified as mild, but later they died. The second group is patients with heavy onset who later died. It was a group of patients with sum of points from 3 to 5, and there were 16 patients. The third group is recovered patients with light onset. Their total score was 0 or 1. Patients were discharged from the hospital in a satisfactory condition. There were 970 patients. And the last group, recovered patients with heavy onset, their total score was 3 and 4. They were discharged from the hospital in a satisfactory condition. There were 112 patients. There were no severe patients with a total score of 5 who recovered. After dividing into groups, a calculation was performed for each group according to some indicators such as duration of hospitalization, age, body mass index, systolic and diastolic blood pressure, and others. In order to find differences among groups in general, we used Kruskal-Wallis test. This test is used to evaluate differences between more than two unrelated samples simultaneously according to the level of a particular attribute. Graphs on the slide show the indicators included in the scale, I mean the CORP65 scale. For all indicators, the p-level is less than 0.05. Therefore, there are statistically significant differences. But the Kruskal-Wallis test showed differences in all groups in general. However, group 1, I mean patients with late onset who later died, is of interest because these patients were classified as mild, but later they died. So it's necessary to determine which factors can lead to death. To assess differences between group 1 and group 3, light onset death and light onset recovered, we used the method of multiple comparisons of mean ranks. Table 1 presents those indicators for group 1 and 3 for which there are statistically significant differences. The data are presented at the median and the first and the third quartiles. According to the table, it can be noted that a decrease in systolic pressure, an increase in respiratory rate and heart rate, a decrease in saturation and hematocrit, an increased level of bilirubin and segmented neutrophils indicate an increased probability of death of a patient. Systolic blood pressure and the respiratory rate are already included in the CORP65 scale. However, other indicators are not involved in it. So, in the presented study, we have performed a retrospective analysis of 1412 case histories of hospitalized community-acquired pneumonia patients in all hospitals in the Tomsk region in 2017. All patients were categorized into different groups based on lethality and CORP65 score. According to the Kruskal-Wallis test, the groups have statistically significant differences on the indicators included on the scale. However, there was a group of patients who were classified as mild on CORP65 scale, but who later died. Two groups of patients, recovered and dead patients classified as mild, were compared with each other to determine the factors that can increase the probability of occurrence of death. Significant indicators of an adverse outcome were identified. Thus, it is necessary to modify the scale and take into account a larger number of indicators for a more accurate classification of patients when they are admitted to the hospital. So, thank you for your attention. That's all.
Thank you very much. Any questions, please? We don't have a question. May I ask you a little question? I'm not a specialist in the methods of analysis, but at the last table, please. The row about hematocrit, in the first column, the number 31 is presented. As it is known, the normal hematocrit is near the 40. Yes?
Mm-hmm.
You understand my question?
Yeah. But what is the question?
What? This level of hematocrit, 31, is it typical for the disease?
I guess yes, because these patients have community-acquired pneumonia, so they can't. No, they can have a normal level of some indicators, but I guess they are different from normal level for healthy people.
Thank you. Thank you very much. Any other questions? No? Okay. The next presentation, it is my presentation. Thank you, Alexandra. So I must share my screen. One moment, please. Sorry. Have you seen my presentation?
Yes, of course.
Thank you. So I will start. My presentation is devoted to the one-dimensional non-Newtonian models of arterial thermodynamics.
Герасим
And
Vladimirovich, can you full screen mode?
oh, sorry. One moment, please. Okay.
It's okay, thank you.
Okay. The presentation is devoted to the mathematical modeling of blood flow in the arteries in one-dimensional case. Such models are constructed by the averaging of the three-dimensional equations of hydrodynamics on the vessel cross-section. As it is known, blood is a complex incompressible media which consists of the fluid part, which is called plasma, and different blood cells. The presence of these blood cells has a major impact on the mechanical properties of blood. As it is demonstrated by the experiments, blood is a non-Newtonian fluid. Its viscosity is a non-constant in comparison with the case of the Newtonian fluid when it is constant. The dependence of the strain stress on the strain rate for the non-Newtonian fluids are nonlinear in comparison with the case of the Newtonian fluids when it is linear. Dimensionless velocity profile for the non-Newtonian fluid is flattened in comparison with the case of the Newtonian fluid when it is parabolic. Unfortunately, in most of works on one-dimensional models of blood flow, the non-Newtonian behavior of blood is not considered. So the main aim of the presented report is to construct one-dimensional models of blood flow with the non-Newtonian nature of blood and to obtain its analytical solutions. At this slide, the general model of blood as is presented. It consists of incompressibility condition, motion equation, and the rheological equation. The rheological equation for the viscous part of the stress tensor is considered as a model of blood as a non-Newtonian fluid. This general system can be averaged on the vessel cross-section and is reduced to the system of two partial differential equations on three variables. A is the cross-sectional area, Q is the flow rate, and P is the pressure. It is the system of two equations on three variables. So, to complete statement of the problem, the so-called equation of state must be added to this system. For the arteries, the equation of state represented by equation 8 is used in most works in literature. The non-Newtonian behavior of blood is modeled by the so-called frictional nonlinear team in equation 6. At these slides, the models of blood as a non-Newtonian fluid are presented. At first, the case of the Newtonian fluid is considered. For this case, this constant coefficient, it is dynamic viscosity. A wide class of non-Newtonian models is the so-called generalized Newtonian models. It is constructed as the generalization of the equation for the Newtonian fluid. For the case of the variable dynamic viscosity. And the white class of these models is the models with two asymptotic viscosity. It is represented by equation 11. At this slide, the first non-Newtonian model is presented. It is the so-called power law model. This model is widely used in non-Newtonian fluid mechanics. For this model, the frictional term is presented by following formula. At this slide, so-called cross model is presented. It is model with two asymptotic viscosities. For this case, frictional term is presented by equation 16. And Karo-Yoshida model, it is also model with two asymptotic viscosity. And for this case, frictional term F is presented by equation 18. And the last model is so-called Yeliss-Varadkar model. For this case, a frictional term is presented by equation 20. As it can be seen for all of these models, this frictional term, viscous term, is a complex nonlinear function on variables Q and A. And in the coefficients of these functions, the values of dimensionless velocity are presented. The dimensionless velocity is modeled by equation 21. And as it can be seen, the flattened profile, which is typical for the non-Newtonian fluid, is can be modeled by a variation of parameter there. After the dimensional analysis, the system can be reduced to the following system. As it can be seen, there are two dimensionless parameters in this system. It is parameter He and parameter epsilon. For the arteries, parameter He is not small, but parameter epsilon for the arteries near the heart can be considered as small. And at a distance from the heart, it is increased according to the viscous friction. For some types of vessels in the model, the small parameters exist. So the perturbation method can be used for the analytical solutions of the problem for such system. In the presented report, we consider very simplified problem for the case of the infinite vessel. If the infinite vessel is considered, so only initial conditions must be stated, and the boundary conditions are not considered. According to the perturbation method, initial conditions are presented as a series on the degrees of small parameter epsilon, and the solution of the problem is obtained in the same type. In the presented report, we consider the terms only up to the second order of epsilon. The following parameters are considered and following values of initial functions are used. Oops, sorry. For the first perturbation, for the first degree of epsilon, the following system of partial differential equations is considered. It is the system with the constant right part. And for the second perturbation, the same system is considered, but with the case of the non-constant right part. Problems for these systems are solved by well-known methods, which are applied to the first-order systems of partial differential equations. The method is based on the introduction of new variables and simplification of the system. At this slide, the plots of the solutions as functions of time and coordinate are presented. As it can be seen in the plot of Q, the damping of the solution takes place with the increasing of time. It is the main reason of this is the presence of the viscosity. And at this plot, we try to compare the presented models as at the fixed value of coordinates. So the solutions are considered as time functions. The viscous models are compared with the case of the inviscid model when the viscosity is ignored. As it can be seen for the viscous model, the damping with the increasing of time takes place. And some models behaves such as Newtonian fluid, and other models demonstrate stronger damping and another behavior. At this slide, the plots of the solutions at a fixed value of time are presented, and the same behavior takes place. So in the presented report, we try to construct non-Newtonian one-dimensional models of blood flow and to obtain its analytical solutions. These analytical solutions can be used for two reasons. At first, they can be used for the comparison of various non-Newtonian models. And at second, they can be used for the numerical test as a numerical test of the programs which realize numerical algorithms. For the realistic situations, the problems for considered system can be solved only numerically. So if we try to program the numerical algorithms, we need a test. So thank you for your attention, and I'm ready to ask the questions.
Gerasim Vladimirovich, can you show the picture with initial condition? Звук выключить. Полностью надо. Gerasim Vladimirovich, can you ask can you show the slide with initial condition?
Okay.
In initial condition, in practice, when we see blood is filled vessel in real situation, it's pus, okay? Maybe equation initial maybe contain trigonometric theory.
Yes, that's all your question.
Yes. Can you do some research in this?
I understand your problem. This type of initial condition, it's the only simplification which is used for obtaining of analytical condition. In real situation, yes, the models of the initial conditions for such functions can be approximated by the sums of trigonometrical functions or Fourier series or any other type. This form is only proposition for the obtaining of analytical solution.
Thank you. And I have one question to else. The first. I think in medical literature, we can find a lot of data of real fell blood in a real vessel. Maybe we can compare the result of model and real result. For example, using rock analysis or something else.
Yes, yes. But it must be noted, нужно заметить, that one-dimensional models are used for the cases of the systems of blood vessels, то есть для систем кровеносных сосудов, конечно, не для отдельных сосудов. And there exists works where the results of the numerical analysis are compared with the results of the experiments, and the results are compatible.
It's very interesting. Thank you very much.
Thank you. Thank you for your question. Any other questions, please? No. So, я отключу демонстрацию. And our next presentation is comparison of the strain or the stress strain state of the human eye after some surgeries. Please, you are welcome. Please introduce yourself. Да, микрофон.
Hello,
Hello.
can you hear me?
Yes.
I'll try to open my presentation. Hello, my name is Lyudmila Vinatovskaya, and I'll be the keynote speaker today. The theme of our report is comparison of the stress-strain state of the human eye after PARC, LASIK, and SMILE surgery. This work was proposed by ophthalmologists of St. Petersburg branch of the Fedorov Eye Microsurgery Federal State Institution. And they asked us to develop biomechanical models of the cornea after modern refractive surgeries such as SMILE, LASIK, and PARC. So the aim of our research is to construct finite element models of different laser vision correction procedures to assess changes in the stress-strain state of the cornea after surgical correction of myopia. In other words, for correction of nearsightedness. It is known that the cornea has a complex biomechanical structure and consists of 5 main layers of different thickness and different biomechanical properties. The stroma is the thickest layer of the cornea, and here you see it. And it is placed between two thin but very strong membranes, Bowman's membrane and Descemet's membrane. Corneal stroma is composed of flattened lamellae, you can hear them, layers of collagen fibrils, and experimental studies indicate that the material of the cornea, as well as material of the sclera, is highly anisotropic and heterogeneous. Currently, LASIK surgery is considered one of the most popular types of surgeries for the correction of various refractive errors. And since 2007, the new flapless surgery, SMILE, namely the removal of lenticular tissue through a small incision, has occupied a significant niche in modern refractive surgeries. According to ophthalmologists, nowadays more than 85% of refractive surgeries is laser surgeries and 82% of those is SMILE. Significant advantage of SMILE over LASIK and PARC is painlessness, safety, speed, and comfort. In SMILE procedure, there is no pronounced pressure on the eyeball like in LASIK surgery, and unpleasant odors and sounds specific for the stage of laser ablation as in PARC surgery. Thus, SMILE is promising and modern way of correcting myopia with fast recovery of visual acuity without additional correction like in LASIK and absence of corneal flap as in PARC surgery. Recent studies have widely discussed the potential biomechanical benefits of SMILE over LASIK and PARC. It is also mentioned that Bowman's membrane and anterior stromal lamellae remain intact after SMILE, while in LASIK and PARC, Bowman's membrane either is soft, like in LASIK, or ablated, like in PARC surgery. So it means that differences in laser methods and multi-layer structure of the cornea should be taken into account in mathematical modeling. The corneal scleral eye shell is modeled as joint spherical segments with tapered thickness. Here you can see how the thickness is changes. Cornea is modeled as multi-layer shell with 4 layers. The first one layer represents epithelium, The second layer represents Bowman's membrane, the third one stroma, and the cement membrane. Sclera is modeled as monolayer with bigger radius. It is assumed that the composite shell is filled by incompressible liquid with true pressure P0. Nonlinear analysis is performed by means of engineering simulation software ANSYS. Due to the symmetry, two-dimensional modeling is performed with finite element plane 182. The axisymmetric problem is considered with axis of symmetry Y. The axis is directed to along the normal to the surface of isotropy. At the top of the cornea, the symmetry conditions is applied, and the lower border of the sclera, the displacements in the vertical direction is prohibited. Nonlinear solution, including large deflection effects, is performed. Here you can see our models of 3 surgeries. LASIK surgery procedure consists in cutting a thin corneal flap. Here you can see it in our modeling. The first stage, the flap is formed. At the second stage, the inner surface of the cornea is subjected to the laser beam. Then the flap is placed back, and after such surgery, an additional layer flap appears. SMILE procedure means the technology of extraction of the lenticular, here you can see it, through a small incision. The surgery is fully performed by femtosecond laser inside the cornea without affecting its surface layers. So the difference between two surgeries, you can see here a small cut in LASIK surgery, and this cut is absent in SMILE surgery. PARC procedure, it is a procedure in which a corneal flap is not cut and the corneal cup is not formed. The cornea is immediately exposed to the laser ablation. SMILE and PARC technologies don't have a corneal flap, and therefore they are called flapless. In our simulations, the effect of following parameters on the stress-strain state of the eye is analyzed. The diameter of the lenticulum, it is the same as ablation zone in LASIK and PARC. Here you can see it. The lenticular thickness and ablation thickness in LASIK and PARC are similar. The diameters of the cup in SMILE and LASIK are the same, and the thickness of cup in SMILE or corneal flap in LASIK are the same. Materials of the cornea and sclera are transversally isotropic. Also, we assume that elastic moduli of each layer of the cornea in normal direction are taken 20 times less than in tangential direction. Here you can see the parameters of the main layers of the cornea, and you can see that Bowman's membrane and the cement membrane are very thin but very strong membranes. Here you can see sclera parameters. The layer which represents the lenticulum and ablation zone, also wound cuts, are modeled as similar layers and considered as very soft material. The next slides show the stress-strain state of the cornea before surgery and after SMILE, LASIK, and PARC surgeries. Internal pressure is taken 50 millimeters of mercury. The results of the numerical simulation show that after surgical correction of myopia, flexural rigidity of the cornea reduces significantly. We can see that after LASIK surgery, the apex of the cornea has a greater displacement than after SMILE and PARC. In this slide, one mesostress distribution is presented. We see that horizontal cuts, like in LASIK and after SMILE, reduce stress in corneal flap, and area above the cup in smile surgeries. In LASIK model, the stress increase in the stroma, here you can see stroma, is greater than in SMILE and PAC models. A similar result is observed in the case when a much larger optical zone is used. In other words, when more material is removed in PAC and SMILE surgeries. These results are consistent with clinical results, and we can say that advantage of SMILE is that with the same initial data, with its help, the high levels of myopia may be corrected compared to PAC surgery. In this slide, the fragment of the cornea after LASIK surgery is shown. It is seen that the maximum stresses occurs in Bowman's membrane. Here you can see it, Bowman's membrane. This part of flap, this is wound cut and Descemet's membrane. This effect that largest stresses appears in Descemet's and Bowman's membrane are true both for before surgery and after surgeries. So we can say that Bowman's membrane and Descemet's membrane plays an important role in biomechanics of cornea. The main results I've told already, but I've already told the main conclusions. They are presented again on this slide. The main idea is that SMILE and PAC may be considered equivalent in terms of biomechanical stability. Here you can see the literature. In the first paper, a good overview of different mathematical models of LASIK, PAC, and SMILE surgeries are presented with literature on from our different ophthalmologists and on biomechanics. Thank you for your attention.
Thank you for the interesting reports. Any questions, please?
Ludmila, I have one question. Can you show me the slide with the 4 picture of stress?
Mm-hmm. Yes.
Can you ask me why dark blue isn't it in the high of after PRSK? P-I-K-E.
You means why you don't see the blue?
Yes, dark blue. Yes, dark blue in high.
Okay, I'll explain it. Because this area is subjected to the laser during the surgery. And these layers are so soft that when our shell deformates, they become like a small surface and you can't see them under deformation. It means that they are disappeared during the surgery, so you can't see them. These layers just slip under pressure. So these models can explain are very suitable for such refractive surgery and surgeries.
It is interesting that there is no after LASIK and there is no after SMILE.
Because after LASIK and after SMILE, the flap, this area just become a small line, blue line.
Yes, of course. Okay, I understand. Thank you. Thank you very much.
Any other questions? So, thank you, Ludmila. And our session is over. Большое спасибо докладчикам за интересные доклады. After 15 minutes, the next session will be started. So, thank you.
Thank you very much.
Thank you. Thank you.
Thank you.
Если жизнь нас осуждает, как уже его сбегали, что кого-то всегда рисковать, как уже его сбегали, что всегда рисковать. Зачем известность громкой, известность свою предпочесть, чтобы знали рядом, знали потом, что друга есть. Чтобы знали рядом, знали потом, что друга есть. Юность свою повторить, юность свою повторить, свои сердца, что пока рассчитаны на часть примера, что пока рассчитаны на часть новых мира, очень много тех, кто призывает творить, открывать, мы проводим пути, пока не нам тосковать, мы проводим пути, пока не нам тосковать. Когда своим сердцами на ладонь положит земли, что покрасом рассчитаны два, и жальцы новых мирам корабли, что покрасом рассчитаны два, и жальцы новых мирам корабли, что покрасом рассчитаны два, и жальцы новых мирам корабли.
Ага.
Уважаемые докладчики, здравствуйте.
Герасим, сейчас. Это какая секция у нас?
Все правильно, Олег Игоревич, все здесь.
А,
Вы председатель, я буду
да-да.
модератором у вас.
Хорошо, хорошо, хорошо.
За техническими вещами буду следить.
Ага,
Ага. Можно мне будет несколько слов сказать?
да-да, да.
Сперва, да? Ну, как вот 11 часов будет, тогда мы начнем. Да?
Ага.
Аня, здравствуйте.
Здравствуйте.
Так,
Здравствуйте. И всем здравствуйте.
пока никого не слышу, у меня что-то звук не подключился.
Всем привет.
Здорово. Как дела, Владислав?
Нормально.
Хорошо.
Так, 11. Ровно.
Ну что, коллеги, 11 часов.
Да.
Давайте начинать. Значит, мне нужно несколько слов будет сказать. Good morning. My name is Gerasim Krivovichev, and I am a moderator of this session. Today we have at the first part of the session 5 presentations. All presentations must be made in English. No more than 12 minutes are given for presentation. And before 2 minutes of this time, I will inform you about it. And 3 minutes are given for the questions. During the presentation, all microphones, the audience will be muted. And after the presentation, you can unmute yourself and ask the question. Also, the questions can be asked in chat, in YouTube or in Zoom. Ну и по инструкции я должен по-русски это все повторить. Меня зовут Герасим Кривовичев, я являюсь модератором этой сессии. Значит, у нас сегодня в первой части будет 5 докладов. Значит, все доклады нужно делать на английском языке. На доклад отводится не более 12 минут. За 2 минуты до конца доклада я должен сообщить докладчику об этом. И 3 минуты отводится на вопросы. Во время доклада все микрофоны, кроме, естественно, докладчика, будут включены. И если вы хотите задать вопрос, нужно будет включить микрофон. Также можно задавать вопросы в чате, в Zoom и в YouTube, где у вас идет трансляция. Ну и я их буду озвучивать. Вот. The session is chaired by Professor Олег Игоревич Древотин and Professor Anna Gennadievna Golovkina. Let's start. And our first presentation is optimization of a real-time stabilization system for the MIMO nonlinear maglev platform.
Hello, can you hear me?
Yes.
Okay, so I'm starting.
Please share your presentation.
Sure. just a second.
Сергей, да?
Yes, it's me.
Okay. We can see and hear you. But
Okay, so this work is titled Optimization of a Real-Time Stabilization System for the Multi-Input, Multi-Output Nonlinear maglev platform.
Не слышно.
Сергей, да, вас не слышно.
Oh, I'm sorry. So this is task about maglev platform levitation, and this platform has 4 magnetic suspension. Each suspension has upper electromagnet, bottom electromagnet, and permanent magnet. So this platform has 4 permanent magnets to compensate the large part of the weight of the platform. And also I should say that this task is quite non-linear because in such range of the gap, if we near to the magnet, it means for us that we have greatly increasing their force. Also, permanent magnet is a quite non-controllable part of the system. So basically, the distance between bottom electromagnet and top electromagnet and between rails should be about 5 millimeter. So it means the distance between up and bottom should be 5 millimeter. So the idea is which equation, which algorithm, which controls should be implemented in the hardware electronic chip to provide active real-time feedback control for this platform, to provide the levitation. And to describe the dynamics, we use 3 Euler angles and also 3 their velocity. And the equation which connect each other is nonlinear and presented in the work. So here you can see the observer vector, which is a signal to the controller, to the hardware implementation. And you can see the control signal, which might be treated as a voltage to each electromagnet. So it means the control system can observe 4 gaps for each suspension, and control system can provide in real time the control system which is applied to the control coils of electromagnets. Here you can see the optimization model, and a bunch of the trajectories is widely known and widely applied in the control problems. So we also choose to try to solve this problem based on the bunch of the trajectories. And this model of optimization is combined the equation for the object, and the vector x has dimension about 10. And this model combined the equation for controller with matrices A by C, B by C, C by C. That means matrices for controller. And this should be calculated in a hardware electronic chip in real time. So such controller is a dynamical dynamical controller, which has their own vector of state, and its dimension might be various, might be different. I made a reference to the work which we propose how to select the difference, how to select the dimensions of such controller. Next, we can see the quality criteria, which is estimating all bench of trajectories, where capital N is the number of the trajectories in the bench in the computational experiment. And the idea is how to calibrate the components of the matrices of controllers, which should be used in the digital program, in the digital algorithm. To solve this problem, we provide and we propose to use parametric optimization approach. In the paper, we presented some analytical work, and we obtained the gradient of this controller and provided the gradient minimization. So formula number 7 and equation number 8 is presented the gradient of the functional, which can be implemented in the optimization program. So on this slide, it's presented the optimization and simulation results. On the left, you can see the trajectories before optimization, on the right after optimization. On the top, you can see the trajectories of the gaps, of the 4 gaps. And on the bottom, you can see the trajectories of the control signal. So we achieved, we increase the quality of gaps trajectories, and at the same time, we achieved the quality of control signals. So it means the quality of stabilization criteria and the criteria of control signals makes better. So the non-linear multi-input, multi-output control system for maglev levitated platform was optimized, and stabilization was provided based on the non-linear models and based on the bench of the trajectories which were optimized. And the controller has a dynamical structure and should be implemented in the digital real-time control system. I mean some digital chip, some electronic device. Such controller includes their own state, their own vector of state. It means such controller includes some filter, for example, Kalman filter, and works in multi-input, multi-output mode. Okay. I can answer on the question.
Thank you. Questions, please.
If there is no question, I can ask.
Okay.
Is your optimization problem is convex?
What do you mean convex? I forgot what
Э,
does.
Ну,
Выпуклая.
я имею в виду, что функция, которую ты оптимизируешь, она выпуклая или нет?
I think it's need to be investigated. It's
And
complicated.
what optimization algorithm did you use?
It's simple gradient optimization.
Okay, thank you.
Mhm.
Any other questions, please? No? No. Okay, and our second presentation is on a new approach to RFQ channel optimization, and the speaker is Oleg Igorevich Trivotin.
I want to demonstration, but
Это
I
ваш экран?
can no. Previous reporter should turn off presentation.
Сергей, закройте, пожалуйста, остановите демонстрацию экрана.
Да, секундочку. Ага.
Герасим Владимирович, а вы можете ему сами обрубить.
Ага, сейчас делаем.
Надо открыть.
Так, дополнительно, да, Аня? Все. Правильно?
Да, там вверху экрана настройки, по-моему, просмотра можно... Ага.
Ну, всё. Да, демонстрацию экрана, пожалуйста, включите, Олег.
Видно.
Окей, start.
The report is on a new approach to RFQ channel optimization. This problem is considered as an optimal control problem for an ensemble of dynamical system described by density distribution of in-the-phase space. Previously, for a numerical solution of this problem, methods using the first variation of the trajectory were applied. At the present work, a method based on the second variation of the trajectory is proposed. This report is devoted to application of this method to the problem of RFQ channel optimization. This method allows computing not only the first derivatives, but also the second ones. RFQ quadruple structure was invited by Soviet physicists Kapchinsky and Teplikov, and they proposed an algorithm of the channel design based on the adiabatic bunching, which is widely used now. The RFQ structure is applied widely because due to its ability of accelerating bunching and focusing of a low energy beam simultaneously. In 1980, Ovsyannikov suggested to search for accelerating structures by optimal control theory methods and developed an indirect first-order method of beam dynamic optimization based on known numerical methods of optimal control theory. This method was successfully realized in works of Ovsyannikov and his followers. In the adiabatic bunching method, phases of the particles vary very smoothly, and it is not consistent with the principle of alternating phase focusing, which was proposed by Soviet physicist Feinberg. According to this principle, sharp change of the particle particle phase can provide bunching, focusing, and acceleration. And this principle was successfully used for development of acceleration structures of other types. For example, the drift tube LINAC. To understand whether this principle is also applied for the RFQ structure, we introduced a control model where one of the control functions depends on phase characteristics of the beam, namely synchronous phase, instead of geometrical parameters. And main advantage is that this approach allows to investigate all structures, not only the smooth variation of phase characteristics, but there is disadvantage, a great disadvantage of the first order method. The first order method allows to obtain only the gradient of quality functional. Gradient defines a tangent hyperplane to the surface, separating regions with greater and less values of the quality functional, but does not allow to find direction of descent. In a space of great dimensions and in RFQ accelerator, it may be about some hundreds. Dimension is some hundreds. It leads to serious computational difficulties. Now we proceed to the second order method. It is well-known matrix momenta, which was matrix momenta method was introduced by Soviet mathematicians Gabasov and Kirillova for degenerated control problems. Matrix momenta are components of a twice covariant tensor, which is analogous to the covariant momentum vector. They allow to compute the second variation of the quality functional and to compute second derivatives of the quality functional with respect to parameters when the control is parameterized. After the first order method of beam dynamics optimization was developed by Ovsyannikov, it was proposed to apply a method based on the matrix momentum method in the work of Bablik, Garashchenko, and Kirichenko. But such method seems to be unrealizable for optimization of RFQ accelerator channel because the number of differential equations to be integrated is quadratic on the number of control parameters. But in problems where the dimension of the phase space is small, this method is to work properly, as it was shown by Gorbunev and Lutoshkin. Now we developed the second variation method, which is based on expression for the second variation. This method is described in these two works. And now I explain the essence of this method. Consider controlled dynamical system. And the first variation of trajectory of such system is given by a well-known expression 2, where G is the green function which satisfies to the equation 3. The second variation of the trajectory of this dynamical system can be written by analogous way as it was shown in these two works. This expression 4 contains tensor D, which has the following expression, and it is satisfies to the differential equation 6. Now we proceed to problem formulation for a beam dynamic optimization. We regard a charged particle beam as an ensemble of dynamical systems described by the equation 1. The particle distribution of the beam is a differential form which degree depends on the bin model. The non-degenerated case is it is correspond to the form, the differential form of top degree, of the top degree, and most degenerate distribution is a set of macroparticles. In this case, the dimension of the supporter is 0, and rho is the sum of scalar functions which values are distant from 0 only at points where particles are located. The density distribution satisfies to follow differential equation and initial condition 7. This is shown in the work which is at the bottom. The problem is to find such control function U that the quality functional reaches minimal value. The RFQ channel consists from 2 pairs of modulated vanes, and we consider it as a sequence of M cells. The equation for phase is 9, and to introduce the synchronous phase, we assume that there exists a particle for which this equation is satisfied at least last few sections, and we call this particle the synchronous particle, and denote it by the index S. When we use the equation for difference between phase of this particle and phase of space modulation, and this equation contained the first of control function U1, the longitudinal component of the electric field intensity can be approximated as woman by this expression, and this leads to the equation of longitudinal dynamics, the second equation of longitudinal dynamics, 12. As a functional, we take the function 30.
Осталось 2 минуты. 2 минуты осталось.
Thank you. The H is a function which is conserved for synchronous particle, at least few sections where synchronous phase does not change. The model is equally applied to various distributions, degenerate or non-degenerated, and for the standard approach consists in approximation of non-degenerate distribution by degenerate, and this method is called by the method of macroparticles. In this case, functional is the sum of this view, of this form. Then we approximate control function by a piecewise constant function, and the functional can be considered as a function of 2 m parameters, and we can find derivatives with respect to the parameters, as in this as here, and also we have equations for conjugate function, and also we can write equations for tensor D, but I do not show because it is very these equations we have, but they are very large, and after that we can find the second derivation with respect to control parameters by the formula 14. Now I proceed to the conclusion. Here we presented the new approach for structure optimization consisting in computation of the first and the second derivation of the quality functional over control parameters. This approach can be regarded as upgrading and refinement of Ovsyannikov approach. It is expected to be more effective as it follows to obtain direction and step of the descent in the process of optimization. But numerical optimization, according to this approach, requires more great effort in programming than the first order method, because not only differential equation for momenta C should be integrated, but also the equations 3 and 6 for tensors G and D. Thank you for your attention.
Thank you. Questions, please.
I have a question.
Huh?
Oleg Igorevich, I actually didn't get from your presentations what is the benefit of using the second order variation method in comparison with the first order method.
The second order method allows to find the descent direction, because the first order method in the first order method we can find only gradient which define the tangent surface to the tangent hyperplane to the surface of constant value of functional, and not direction. And to find direction is very great problem. When we know gradient, it is very difficult to find direction of descent in the space of great dimension. And the second order method give us this direction if we use the second derivatives. We can yes.
And maybe you justified your conclusions by some calculations of comparison to methods.
Louder, please.
Did you justify your conclusions of benefits of the second order methods by some calculation to compare it with the first order?
It is very great problem, and I have not such calculations and computations. And I think that it will be in the future.
Okay, thank you.
Okay, any other questions, please? No? So thank you, Oleg Igorevich. And our next
how I should
там остановить презентацию просто будет.
Остановить. Как остановить? Где это находится?
Вы наведите наверх на самой мышкой.
Сейчас.
Себя, и там такая полосочка выскочит.
Сейчас. Наверх. Остановить. Нашел. Все.
Our next presentation is influence of dyes on the electro-optical properties of liquid crystals. Tatiana, let's start.
Okay. Let me share my screen. Can you see my presentation?
Yes.
Okay, so let me start. My topic will be about the influence of dyes on the electro-optical properties of liquid crystals. So, liquid crystal compounds and their colored solutions in last years are interesting because such compounds are the main components of industrial liquid crystal displays. The properties of composition are determined by orientational order mechanism upon transition from isotropic liquid state to a mesophase. In turn, the properties of the mesophase in cooperative system depend strongly on ability to self-assembly of its constituent chemical compounds. If the mesogen forms an intermolecular complexes of various structural types, the effect on the spectral properties of the dye will also be different. The shift and splitting of the band's mineral impurity dye molecules placed in the liquid crystal gives an indicator of the mesophase structure. It is very important to study the structural features of liquid crystal of ER and UV spectroscopy methods and computer modeling with respect to equations of quantum mechanics. Next slides show the quantum mechanical method for solving this problem. We use density functional theory where the central physical quantity is the electron density rho, which depends on the coordinates of all electrons. The energy of ground state of the molecule is described by the electron density functional E, and the energy is minimal if rho is the exact electron density of ground state. The total energy is calculated with the hybrid functional B3-LIP. It is one of the most popular correlation functional proposed by Li, Yang, and Parr. Here ABC are constants selected from experimental data for set of relativity simple chemical compounds. In our work, the most favorable equilibrium geometry of the entire system is found by Newton-Raphson and gradient methods. These tasks require large computer resources. The non-stationary theory of the density functional TD-DFT is based on the fact that for a given initial wave function, there is a single mapping between time-dependent external potential on the system and time dependence of the density. The configuration interaction method takes into account the set of different configuration of the allocation of electrons at the main and vital levels. The configuration interaction singles method include only single excited states. To simplify the calculation without much damage, we can limit the number of configuration taken into account by setting a certain number of occupied and vital orbitals. The intensity of the absorption band in the electronic spectrum is determined by the strength of the oscillator. Complexes formed by liquid crystal molecules were investigated with dye molecule using density functional B3-LIP 631G method, which takes into account the indirect effect of electron colorations. The equilibrium geometry of study structures are determined by full optimization of geometry. There are no imaginary frequencies in the study structures, which indicates the stability of the found configuration. So dye molecules with optimized geometry are shown on figures 1, 2, and 3. The dipole moment is a very important characteristic of the formation of liquid crystal structure. Table 1 shows the total energy dipole moments for these molecules in vacuum. Complexes with dye molecule, which were found by the geometry optimization, showed on the figures 4 and 5. Dye molecule, here it is, and monomer CB5, this is a liquid crystal, lay in the same plane at the distance 2.21 angstroms. In other case, on the figure 5, dye molecule is perpendicular to the main axis of liquid crystal. The main criterion for selecting models for further research was that these structures have the minimum absolute value of total energies. Thus, their presence in the mesophase is most likely. The table 2 shows the total energy the energy of intermolecular interactions, and the distance between the atoms of liquid crystal, molecule, and dye. The electron spectra is sensitive to associate structures. The electronic absorption spectra of complexes with dyes and liquid crystals for their optimized structures were investigated by TD-DFT method. Communication is carried out due to the dipole-dipole and donor acceptor interaction between two molecules. We can see that received changes in the electron spectrum of the dyes depending on the liquid crystal. Transition between energy levels of molecular orbitals and their frequency performed in the table 3. The frequency of the basic high intensity transition corresponds to the transition from the highest occupied molecular level to the lowest unoccupied molecular level. The value of the wavelengths and intensity for similar transition changes for the complex CB5 with dye molecule. The intensity of the dye band increases strongly upon interaction with CB5. We can see it in, for example, in this table. So let's summarize the work done. The different molecules of liquid crystals, such as they are performed here, and their interaction with different dyes were investigated by the density functional theory using hybrid potential method. The electronic absorption spectra of isolated dye molecules and the resulting complexes with liquid crystals were calculated. It was shown that the shift of the absorption bands in the spectra of the dye depends on the structure of the complex. When the mesogen forms an intermolecular complexes of various structural types, the influence on the spectral properties of the dye will also be different. And the shift and splitting of the band minor impurity dye molecules placed in the liquid crystal gives an indicator of mesophase structure. So thank you for your attention. And what about your questions?
Thank you. Any questions, please?
I have a question. What software did you use to perform your calculations?
We use Gaussian program.
And did you consider any problem of optimization of the structure of these molecules to achieve some desired chemical characteristics? I don't know.
Of course, there is a lot of problems. So we present here the most favorable structures because it is not too easy to find them and to construct in order to intermolecular forces, because we have to find the optimal position between them, for example, and after that sometimes we have computational problems. In order we test different methods which I performed here. So this is a TIS method, the TD-DFT, and different types of them. Our result was were performed here with TD-DFT method, but we get almost the same result using some others. And it is interesting to test them and to find maybe the difference between them, because it is not the same approach for them.
Okay. Thank you. But is it feasible to implement some optimization approaches in your Gaussian software? Or it's open code or it's closed code?
Yes, it is closed code, but we can. What we can do, we can choose the method where we can work with our molecules, for example, for our structures, when we can prepare them before entering with Gaussian, or we can combine different methods in it, maybe, and according with it, we get the result, because code is closed in Gaussian. But we have it is the best product for this calculation. That is, we use it.
Okay, thank you. Thank you for your presentation.
Sure. Any other questions, please? No. So we must wait 3 minutes. Аня,
А?
подождем 3 минуты до следующего доклада, да? Регламент.
А какой следующий доклад?
Ну, видимо, ваш, я не знаю.
Да.
А, мой?
Да.
Ну, давайте подождем.
Ну, вчера Хватов ждал просто.
Я старалась успеть.
Хорошо, молодец.
Ну, я могу начать, потому что я могу не уложиться просто.
Можно начать.
Okay. And our next presentation is a model-based optimal control of transmutation strategy in accelerator driver system. The speaker is Anna Gennadievna Galukina. Please, you are welcome.
Okay, I hope it's visible. Okay, so my today talk is dedicated to model-based optimal control of transmutation system in accelerator-driven system. And first of all, I would like to say several words about the motivation of this research. I think all of you know that the most critical problem of nuclear energy is the production of radioactive waste. An average power plant creates about 20 metric tons of waste per year. And for example, in Russia, there are 37 such nuclear plants. That means 740 metric tons of waste is produced every year. That's quite a large quantity. And how this problem is solved nowadays? Nowadays, spent fuel is classified and placed in geological waste repository deep underground. But as you can see from this picture, the main problem of this storing approach is that nuclear waste contains a lot of long-lived isotopes. These isotopes include fission products and transuranic elements. And as you can see from this slide, the long-term radiotoxicity is dominated mostly by plutonium and other actinides, corresponding to the blue and red line on this picture. This level becomes equal to the radiotoxicity of uranium ore only more than after 100,000 years after the fuel was discharged. This means that the safety of this geological repository should be provided for more than 500 years. And this is quite a long period of time. And I think that we can be 100% sure that the storage will be safe during all this time. But what we can do? Preliminary treatment of nuclear waste potentially can reduce the disposal time by 4 orders of magnitude. As we saw with plutonium and other transuranic elements, they give the main contribution to the long-term radiotoxicity of waste. So first of all, these isotopes should be separated from the others. And after then, we can try to convert them into short-lived or stable by neutral or charged particle fluxes. This process is called transmutation, and I will focus on this further in my presentation. The facility to perform this transmutation we will consider as accelerator-driven system, which is now one of the promising types of advanced recycling reactors. Its main parts are the proton accelerator, spallation target, and subcritical core. Due to the core subcritically, this let us introduce some atypical actinide mixtures inside it, because the external neutron supply necessary to maintain the nuclear chain reaction inside the core comes from charged particle beam interaction with the target. Our goal with respect to this physical problem is to minimize the radioactivity of spent fuel by the time moment t, capital T, which we denote the end of the company. And we try to solve this problem using optimization technique. So we want to define the amount and the composition of charged fuel in the initial moment of time in order to achieve the minimal radiotoxicity by the end of the campaign. Okay, now I should switch to the mathematical formulation of this process. And at first we should begin from the mathematical modeling part. So we should build the mathematical model that would further be underlying our optimization framework. So dynamics of fuel isotopes concentration is described by Bateman equations 1 with the initial condition 2. Here I is the index of our isotopes considered in the system, and small n is their total number. Coefficients in these equations, they are found from transmutation chains. So the transitions between our isotopes we considered in our systems. They are constant, and they are evaluated by some EIA organizations, and they are publicly available. Okay, but it's more convenient to operate with these equations when we use the matrix representation of them. So we split the system 1 in 2 parts. We separate it in linear and non-linear parts. The linear part is described by the matrix A lambda, and the non-linear part is described by the matrix A phi. The non-linearity in this matrix comes from the indirect dependence of coefficients in this matrix on the state of the system 3. And from where this dependence coming from, we will discuss now. So nonlinearity of this reaction part has a very complicated structure. It's caused by the strong dependence of the neutron spectrum on the densities of nuclear composition fuel, and then comes from the solution of the equation number 4. That should be solved with the proper boundary conditions. Here we denoted it by 5. Okay. So if we solve the equation 4, we will be able to compute the nonlinear coefficients in our matrix A phi by formula 6. Okay, but in order to obtain these values, we need to solve two-dimensional differential equation, and also to integrate it double time through the energy and through the volume. So it's quite complex, and to get rid of this, we switched to multi-group approximation of our equation 4. It's widely used to discretize the continuous energy variable corresponding to the energy in the range from minimum to maximum energy. If you write down the equation 4 for the Hopf energy group in one-dimensional cylindrical geometry, equation 4 will take the following form, and the boundary condition will be also shifted to the form 8. Now it's simpler to calculate the expressions for the coefficients because to solve these equations, we can use some standard numerical techniques based on finite difference or finite element discretization. And using this, we can also substitute our integration with respect to the energy and with respect to the volume, like Riemann sums, and get the formulas to calculate the coefficients in matrix A phi in the form of 10. Okay, but also during our calculations, we should take into account the constraints on effective multiplication factor. As I said in the beginning of my talk, we want to use a subcritical reactor in order to transmute our transuranic isotopes. Subcritical means that effective multiplication factor in it should be less than 1. So that we need to introduce the additional constraint to our optimization problem that can be expressed by the non-equality 11. But how can we compute this efficient multiplication factor? The mathematical sense of this value is the largest eigenvalue in the eigenproblem corresponding to equation 12. But of course, this means that we should additionally solve this equation at each iteration in order to be sure that we didn't exceed the constraint 11. It involves some additional computational efforts, and we want to get rid of it. So we decided to use physical interpretation of efficient multiplication factor given by the formula 13. Its physical interpretation corresponds to the relation of a number of neutrons appeared in our system to the number of neutrons which is disappeared during the leakage from the volume or to absorption with some isotopes inside the core. Using formula 13 and write down the underlying expressions for each quantity in this formula, we will obtain the representation of our efficient multiplication factor based on n, which we computed previously here. The same quantity we can use for this formula. And if we combine the comparison of efficient multiplication factor computed as an eigenproblem of 12 and approximation 13, we will get a good, quite good coincidence. Moreover, approximations gives us an upper boundary of this equation. So if we use it in the inequality, it guarantees us that we won't exceed the value 1. Okay. Resuming the mathematical modeling part, we can shift to the optimization framework and to describe how we solve it. Optimization model for this problem can be formulated as problem 14, where we want to minimize function f with respect to the given system of differential equations and inequality GL. Okay, f is our cost function characterizing the reductivity of unloaded fuel after time period Tn. In order to get rid of this inequality of our constraint, we want to generalize our cost function and introduce some penalty in the form of logarithmic barrier and just to optimize this generalized function 15 in order to solve our optimization problem. Okay. We tried to use gradient-based optimization methods. Thus, we need the explicit expression for our gradient of the cost function. If we write down it in the form 16, we will see that in order to compute it, we have to calculate 3 derivatives that is here. And further, we will discuss a little bit how I did it. So the first one, okay, I thought that I might be a little bit longer than I try to speed up. Okay, so based on the conditions of the theorem of ODE solutions differentiability with respect to initial conditions, we can find the first derivative in our equations, and if we substitute all the variables, we can come to this formula. Then in order to compute this derivative is quite easy, it's very simple. And in the end, we want to use quasi-Newton optimization algorithm because we have a nonlinear programming problem, and quasi-Newton's methods are widely used in order to solve such problems. They don't require to compute the second derivative, so we just use some approximation that is updated on each iteration by using gradient evaluations. Optimization algorithm is presented here. As an extra neutron source, we used such dependence in order to solve our equations. And in the end of optimization, we came up with these results. So in order to sum up, I would say that after this optimization was performed, it was able to decrease the radiotoxicity of our fuel in 5 times. So a brief summary of my talk is here. I think I won't read it. The most valuable result I already sounded. So by implementing this optimization technique, it was possible to reduce the radioactivity in 5 times. Yeah, thank you for your attention.
Thank you. Any questions, please?
What small n is equal to in your expressions?
What?
What small n is equal to in your expressions? What is the value of small n?
The number of isotopes that I considered in the system. By now I considered around 12 of them,
12.
but in the perspective, it should be considered around 1,000. But I just choose the most valuable one. Yeah.
I didn't understand. Some thousand and small.
Several thousands, yes, of isotopes. Yeah.
Олег Игоревич, that's all?
Can I ask you?
Yes,
Thank you.
Yes.
Thank you.
So please remind, so which computational functions do you prefer in your investigation, in your research?
What do you mean by computational functions?
I mean, some programming aspects, maybe about API. Which API do you use? Do you like for your optimization?
You mean? Do you mean what? In what language I developed my program?
Yeah, for example. Yes. For example.
Okay, I prefer C# to programming, and because it gives opportunity to connect with database system where I store all these coefficients necessary for me for calculations. Yes, and actually I get used to it. So that's my preferable language, and I used it to compute all this stuff.
Thank you. It's clear now. Thank you.
Okay, any other questions? So I want to ask the question. It was a very interesting report, and both questions about the optimization. At first, you use quasi-Newtonian method, and as it is known, it is converges with the good properties only if the initial approximation is close to the possible solution. What you can say about it?
Well, it's a very good question, actually. Yes. So we tried to. Okay, I would start with the beginning. So the problem, optimization problem, is quite complex, and I can't guarantee that it's convex. So it's not guaranteed that we're able to converge to some optimal solution of this problem.
Yes.
Our goal was just to improve and to reduce somehow the radioactivity of waste with respect to the initial loading. We just got such a result, so I don't guarantee that it's optimal one. We just we're able to decrease it somehow. I hope I answered the question.
Короче, сделали лучше, чем было. Вот так, да?
Yes.
My second question was about the unique solution of the problem, but you also answer on this question. Thank you.
Yes,
Thank you.
yes.
It was a very interesting report. Thank you. Any other questions?
Thank you.
Any other questions? No. So our next presentation is an optimization approach for minimization of charged particles orbit deviation in synchrotron and transport channel systems caused by magnetic field tolerances. Длиннее можно было еще назвать. And the speaker is Vladislav. Vladislav, please unmute the microphone.
Yes. Okay.
Okay.
1 second, please. I share my screen. Can you see the presentation?
1 second, please. We wait. We are waiting. Влад, у нас черный экран пока что.
Окей. And now?
Yes, we can see.
Okay.
Let's start. You're welcome.
Okay. In this report, we consider problem of acceleration of charged particles in synchrotrons in presence of magnetic field tolerances. In the case of presence of relative magnetic field tolerances, deviation of trajectories of charged particles may significantly enlarge, and this may cause enlarging beam losses. We discuss the approach of the fast channel parameter optimization technique by using swarm computations and gradient descent for improving the beam orbit. The optimizations aimed at choosing angles of characters elements in structure of acceleration system. For example, at present, the main purpose of the discussed approach is solving the problems related with booster synchrotron of NICA accelerator complex. Equation and problem statement. For dynamics modeling of charged particles in synchrotron and transport channels, we use linear approximation of magnetic fields. In this case, the dynamics of charged particles can be expressed by the following equation. xi plus 1 equals mi xy plus bi. Here x with dot, y with dot are positions and velocities of charged particles. E is the number of magnet elements. M and B are transport matrix and vector, respectively describes influence of corresponding is magnet element on the particle trajectory. Let us call trajectory obtained using this equation with zero initial conditions when x0 is 0 vector as orbit. If the equation is homogeneous and BE is 0 for all E, the deviation of orbit will be 0. The B value is non-zero for some magnet elements, for example, for corrector and sector magnets. Let us discuss the sector matrix, the transport matrix for sector magnet. The matrix M and vector B for sector magnet are presented in this slide. Here, R0 and alpha is rotation radius and angle in horizontal plane. Sigma is the relative magnetic field tolerance. So the sigma is the parameter that causes orbit deviation. When the sigma is 0, there are no orbit deviations. Now let us discuss the corrector transport matrix. It presented in this slide, and here phi and psi are correctors angles and horizontal and vertical planes respectively. L is corrector length. Phi and psi are parameters which we can choose, and these parameters can be used for minimization of influence the magnetic field tolerances on the deviation of BM orbit. So phi and psi are control parameters which we can choose for optimization of orbit dynamics. If the values of relative magnetic fields is 0, the deviation of orbit will be 0. And in the case of presence of relative magnetic fields tolerances, the XE may significantly large. And this may cause enlarging beam losses. To solve the accelerator optimization problem, we need to obtain the two vectors of channel parameters, phi with overline and psi with overline, where here and length of this vector M is the total number of characters elements, and we can formalize problem as minimization with the following fitness function: f from psi with overline psi with overline equals sum of xe in square plus ye in square by the all magnet elements. We use a combination of evolutionary optimization algorithm, particle swarm method, and gradient descent optimization. These methods does not require with numerical gradient calculation. These methods does not require any analytical calculation. At the first stage, particle swarm is applied. Following the original procedure of the particle swarm, we have to create a set of algorithm agents called particles which move in the search space. Each algorithm agent has the position associated with the fitness function arguments, optimized parameters, and velocity, which change on each iteration. After achievement optimization criteria, best position of algorithm agents used as an initial point for the second optimization stage. At the second stage, it is possible to some improve the obtained solution using a gradient descent optimization. Because of using only the particle swarm method does not guarantee achievement of the local fitness function minimum, but it can provide a good initial approximation of the solution. Therefore, the combination of a particle swarm and the gradient descent will always work better than each of them separately. In this slide, we presented results of optimization of trajectory of beam orbit in the booster synchrotron of Nika accelerator complex with taking into account tolerances of magnetic fields caused by deviation of real magnet's length on theoretically calculated. The presence of these tolerances results in significant enlargement of orbit amplitude oscillation. We provide a set of calculation using particle swarm, figure 2, and combination of particle swarm and gradient descent methods to choose angles of characters element, figure 3. As you can see from provided figures, oscillations amplitudes of beam orbit trajectories were significantly reduced by using the above described optimization procedure. For combination of particle swarm and gradient descent, the results is significantly better, as you can see from the figure 3. Conclusion. Results of modeling given above show that optimization of character elements in synchrotron's optic structure by using a combination of stochastic determined optimization methods and evolutionary computations allows to significantly improve beam orbit deviation in the case of presence of tolerance of magnetic fields. Thank you for your attention. That's all.
Thank you. Any questions, please?
How many particles did you consider?
We consider only motion of the orbit. It is only one particle.
Thank you.
Any other questions? No, no questions. Okay. No. Thank you, Vladislav. Thank you. So it was the last report in the first part of our session. And the pause on 15 minutes must be started. То есть делаем на 15 минут тогда перерыв и продолжаем.
17 or 15.
15 до 12:30.
Okay.
Так, уважаемые коллеги, должны продолжать.
Да.
Ага, Олег Игоревич
Да.
здесь на месте.
Let's start.
Let's start. I must say a few words on the technical organization. My name is Gerasim Krivovichev, and I am a moderator of this part of session. And today, at the second part, we have 4 presentations. All presentations must be made in English. No more than 12 minutes are given for every presentation. Before 2 minutes at the end of this time, I will inform you about it. 3 minutes are given for the questions. During the presentation, the audience will be muted. After the presentation, you can unmute your microphone and ask the question. Additionally, the questions can be asked in chat, in Zoom and in YouTube. На русском языке я тоже самое должен повторить. Меня зовут Герасим Кривовичев, я являюсь модератором этой сессии. Значит, у нас сегодня 4 доклада по второй части, которая сейчас стартует. И все доклады нужно делать на английском языке. На доклад выделяется не более 12 минут. За 2 минуты до конца я буду информировать вас об этом. 3 минуты выделяется на вопросы. Соответственно, во время доклада все микрофоны будут отключены, я должен за этим следить. После доклада каждый может включить свой микрофон и задать вопрос. Также можно задавать вопросы в чате. У нас есть чат в Zoom и в YouTube тоже ведется трансляция, там тоже есть чат. The session is chaired by Professor Олег Игоревич Древотин and Professor Anna Gennadievna Головкина. And our first presentation is on the state estimation of nonlinear discrete time models. And speaker is, dear speaker.
Abir is here.
Hi. So I will share the screen now.
Yes, please. Okay, let's start. You're welcome.
Okay. So hi everyone. First, let me introduce myself. My name is Abir Bouaouda. I am PhD student at University of Lorraine in France. I am delighted to be here today to tell you about our paper on the state estimation of nonlinear discrete time models, written by my PhD supervisor, Mr. Mohamed Boutayeb, a professor at University of Lorraine, and me. So, as you are all aware, the state estimation of system is essential to predict its behavior, make a diagnosis, or control it. There are many techniques to estimate the state of a system, but it differs according to the case, continuous time case or discrete time case, and according to the system model and properties. So there isn't a universal method for estimating the state of any system, and that explains the very rich and the varied production of research articles dealing with this problem. The purpose of this paper is to establish a computational approach to estimate the state of multivariable nonlinear time discrete systems. First, I will talk about the discretization of our system. We will use leapfrog discretization scheme. Next, I will look at the design of our state estimator and establish the convergence under some weak sufficient conditions. And finally, we will finish with an application to unmanned aerial vehicles. Let me start with some general information on leapfrog integration. It is a method for numerically integrating differential equations. It is a second-order method. The two main advantages of this technique lie in the simplicity of the model obtained compared to Range-Kutta type discretization, for example, and good numerical stability compared to the explicit Euler method, for example. But it leads to a delay in the state space equation. So let's consider our dynamic system described by a couple of equations of the form x dot equals f of x comma u and y equals j of x comma u. N and p are dimensions of the vectors x, u, y respectively. F and j are nonlinear functions of appropriate dimensions assumed to be Lipschitz. And using the leapfrog formulas, we come to this equation. Xk plus 1 equals xk minus 1 plus 2hf of xk uk. Applying this on our system, we deduce the discretization of our models as follows. Let's now turn to the stability of the numerical scheme. According to this theorem, and as f is assumed to be locally Lipschitz for all bounded input u of t of class C infinity, we guarantee the convergence of the state estimator we're going to develop based on the last discrete time model towards the real state x of t of our system. Turning our attention now to the design of our state estimator. The state estimator proposed is written as follows. X hat k plus 1 equals x hat k minus 1 plus 2hf of x hat k comma uk plus kk times yk minus j of x hat k comma uk. Then the gain matrix kk should be designed so that xk minus x hat k tends to 0 when k tends to infinity. For this purpose, we are going to use an optimization-based approach. So to construct this gain matrix, we try to minimize the series of pk plus 1, defined as follows. Pk plus 1 equals the mean value of xk plus 1 minus x hat k plus 1 times the transpose of xk plus 1 minus x hat k plus 1. Then, after establishing the minimization of the series pk plus 1, we deduce the expression of kk and the other relations to construct this matrix. This leads me to my next point, which is the theorem assuring the convergence of our state estimator. So, under the sufficient conditions, first, f is assumed to be locally Lipschitz, u of t is bounded of class C infinity, and the transpose of the observability matrix times the observability matrix is bounded between lambda min times the identity matrix and lambda max times the identity matrix. And lambda min is positive. Our state estimator constructed by DAS is in the list equations converged. Let me go back to the third condition about the observability matrix. As we define the observability matrix by this formula, Fk and Jk are Jacobian matrices with respect to xk of f and j respectively. We could establish the inequality in the third condition by choosing the Jk matrix, that means the sensors. So based on the observability matrix, we show which physical variable should be merged. That's all I have to say about the design of the state estimator. So let's now turn to an application to unmanned aerial vehicles. The purpose of this application is to estimate the position, attitude, and speed of an UAV by using the state estimator developed above. Before I start, I would like to give you some background information about the study of unmanned aerial vehicles, specifically quadrotors. So, to study the movements of the quadrotor, we use two frames, the inertial reference frame E and the body frame B, linked to the body of the quadrotor. As quadrotor has only 4 motors, it is under actuated system, so the control is somehow more complicated than full actuated system. It's also a nonlinear system. Having said this, designing good state estimator is crucial to control such systems. So to study the quadrotor, we start by dynamic modeling using Newton-Euler formulation, and under some assumptions, the dynamics of quadrotor can be written as follows. Phi theta psi presents the orientation of the quadrotor, and x, y, z the position. U1, U2, and U3 and U4 the control inputs, and the other variables are constants. On this model, we could deduce the state space model for the rotational motion of the quadcopter in the form x dot equals f of x comma u. X is the state of the system, and as that physical variables as position, orientation, or speed could be measured in linear way, we could write y equals j times x. Then we establish the Jacobian matrix Fk. And after calculating this matrix from the state space form, we try to write the observability condition into an explicit form. Therefore, we could determine sensors, the matrix J, so that the observability condition in the theorem is satisfied. I have now come to the end of my presentation. In summary, I spoke about state estimation of class of nonlinear discrete time systems obtained from the leapfrog discretization. It may apply to a large class of systems composed of nonlinear differential equations. However, it's generating delay in the state space equation. In future work, we will be interested in the development of a reduced order state estimator, which could increase the Poisson of attraction, even guarantee a global convergence under some certain conditions. Thank you for your attention.
Thank you. Any questions, please?
Can I have a question?
Yes, yes, please.
So, am I correct that your observer should be executed in some digital controller, right?
Sorry, I didn't get your question.
I mean, so you get the observer, right?
Yeah.
And your observer should be, how to say, should be started or should be run in digital controller of your quadrotor.
So we are talking about simulation?
No, I'm talking about real life and the flight of your multicopter.
Yeah, it would integrated in the autopilot of quadrotor.
I see. Thank you. Good.
Any other questions? No.
No,
So,
may I ask one?
Sorry.
One quick question. You said that you used sensor data in order to identify the metrics of your observer, right? Am I correct?
So I said about sensors. The JK matrix, it's established by sensors. We take measurements from sensors, so we could deduce the matrix JK. So if we want that our observer respects the condition, the third condition, we should select our sensors so that the matrix of the observability matrix is bounded between lambda mean, the identity matrix, and lambda max, the third condition.
Okay, and what kind of sensors do you use? So what do you measure?
We measure speed, position, the orientation. So we are talking about gyroscope. I don't know. GPS maybe.
Okay. Yeah. Thank you.
Okay. Any other questions? No. So our next presentation is a field emitters periodic system on substrate with the electric layer modeling. And the speaker is Professor Vinogradova Ekaterina Mikhailovna.
Good day, dear colleague.
Hello. Please.
Hello, hello. Do you see?
Yes,
yes. Yes, yes.
Yes. Hello, dear colleagues. I am Vinogradova Ekaterina, and our report, Field Emitters Periodic System on Substrate with the Dielectric Layer Modeling. The excellent properties of the electron source using the field emissions are well known. The field emission for a small value of the electrode potential is provided due to the small curvature radius of the emitter top. Thus, the geometric dimensions of the system differ by several orders of magnitude. The single field emitter are used for low energy electron application. Micro and nano-electronic vacuum devices can include dielectrics, for example, as the insulating layers. Dielectrics can also have influence on the field emission characteristic, the most important of which is the current. But the total current from a single emitter, as a rule, does not exceed several microamperes. Increase of the field cathode total current can be obtained by means of a multi-chip system and with extension of the emission area of the emitter. The total current can be calculated with Fowler-Nordheim equation 2. And thus, it is necessary to calculate the electrostatic potential distribution U. In this report, a mathematical model of a multi-chip field cathode as a periodic system of field emitter on a flat substrate with a dielectric layer is considered. Anode is a plane surface parallel to the system substrate. The effect of space charge is neglected. Cartesian coordinate system XY is used to solve the two-dimensional boundary value problem. The field emitter effect on the electrostatic potential distribution is simulated as the effect of the charged line with the charge density tau. Thus, the zero equipotential surface coincides with the surface of the real emitter. The substrate potential is said to be a zero. The anode potential is constant. The other problem parameters are on the slide. To calculate the potential distribution, the unit cell of as a diode system can be considered for x from 0 to x sub 1 and for y from 0 to y sub 2. Due to the fact that the field emitter effect is replaced by effect of a charged line, it is necessary to solve the boundary problem for the Poisson equation form. Let the charged line create a spatial distribution rho in a small volume rectangle phi so that the equation 6 is correct. The solution of boundary value can be written as 7. Functions u sub 1 and u sub 2 are the potential distributions under homogeneous boundary condition 8 and 9. Function v sub 1 and v sub 2 can be represented in form 10 and 11 with the functional coefficient v sub 1 n and v sub n 2. Making use of Poisson equation, it turns out that the functions v sub 1 is satisfy the ordinary differential equation 13, and the solution of this equation is 40. Similarly, the functions v sub 2n satisfy the ordinary differential equation 15, and the solution is 16. The unknown coefficient c sub 1n and sub 2n can be calculated from the additional condition 17 and 18 at interface y sub 1. And for example, in explicit form, the coefficient c are present by formulas 19 and 20. Thus, with the notation 21, the function v sub 1n can be represented explicitly in form 22, and function v sub 2n in form 23. Thus, the potential distribution is found in the entire area of the unit cell of system, and accordingly in the whole region of the field emitters periodic system. In the event when the dielectric permittivities epsilon sub 1 and epsilon sub 2 of two regions coincide, then the obtained formulas are greatly simplified. In addition, as a rule, the charge density tau is presented as a linear function. Then the potential distribution can be written in form 24 and 25. In this case, formula 25 demonstrates the exponential convergence of the series in the drift region of the beam. The condition that the zero equipotential line passes through the apex on the top of the emitter make it possible to calculate the tau value in formula 25. For numerical results, all the geometrical parameters and potentials are taken in dimensionless values. Figure 4 presents the potential distribution and equipotential lines for different distance x sub 1, the distance between the emitter. It is demonstrated the relation of electrostatic shielding to the field emitter array geometric parameters. As the distance between the emitter decreases, the curvature of the equipotential lines in the emission region decreases too. And result, the two-dimensional periodic system of field emitters on a flat substrate with dielectric wire is developed. The potential distribution for the whole region of the field emitter system is obtained in analytical form. All geometrical dimensions and the anode potential are parameters of the field emitter array mathematical model, and the effect of electrostatic shielding on the potential distribution is presented. Thank you for your attention.
Okay, thank you. Any questions, please?
How many terms in the Fourier series should you take to reach required accuracy? For example,
Yes.
one.
Yes, thank you. But as a rule, 10 10 number is all. This is very this number is near the emitter top, the most part of our area, but near the boundary it may be more than 10, near 50 and hundreds, but most part is the near top of the emitter.
Thank you, thank you. And another question. It is interesting to compare this method, numerical method, with method of finite elements. And have you performed such comparison?
Thank you for your questions, but we don't have the experiment for these formulas, but in cylindrical coordinate, we have this experiment, and they are very similar.
Thank you, thank you.
Thank you.
Any other questions, please? No questions in chat? No.
Thank you for your attention.
Thank you, Katerina Mikhailovna. And our next presentation is genetic stochastic algorithm application in beam dynamic optimization problem. And the speaker is Irina Dionysovna.
Yes.
Okay, please share your screen.
Do you see the screen?
Yes, yes.
Thank you. My name is Irina Rubtsova. The report of our collective is Genetic Stochastic Algorithm of Application in Beam Dynamics Optimization Problem. Our report is devoted to beam dynamics optimization problem and the application of genetic stochastic algorithm to its solving. The problem mentioned is being investigated by Professor Dmitry Ovsyannikov and his colleagues, and we rely on experience of this investigation. Now let us see beam dynamics model. The problem of beam dynamics optimization is considered by example of longitudinal beam dynamics in waveguide linear accelerator. The dynamics is described by the equations at this slide. Beam evolution is considered to be a complex of the synchronous particle motion, the equations 1 and 2, and the motion of particles over beam, described the equations of 4 and 5. Along with this model, the Hamilton equations describing longitudinal oscillations of particles near the synchronous one are described by the equations 7, and we introduce the Hamilton function 8 and the separatrix equation 10. Now let us consider beam dynamics optimization problem. The first objective of optimization is to provide the energy of synchronous particle in the demanded interval. You can see gamma sub 1 and gamma sub 2. And the second and third goals are to minimize the energy spread and phase spread at device output. The penalty functionals are suggested to provide this objective minimization. The fourth objective is to maximize the capture coefficient. And the fifth is to minimize the defocusing factor effect at the stage of longitudinal beam dynamics optimization to provide the good focusing. The sixth goal is to provide monotonous bunching of our beam, and this goal is reduced to providing of decrease of mean square spread of particle phases along the structure. And at last, we have the resulting criteria. This statement of the problem is generalized in at this slide. We can consider dynamic controlled process given by these equations. The system 22 determines the program motion, and the system 23-24 describes the dynamics of trajectory ensemble starting from the set m sub 0. We assume the functions to be rather smooth. The quality functional is introduced in the form 26. Now, let us consider the genetic stochastic algorithm suggested by Professor Yermakov. The references are presented at the bottom of the slide, all the references. This algorithm is as follows. At the for the initial generation, we model simulate the random points uniformly distributed in the domain D, and we find the minimal point. After that, we select the best points among the generation points, and we obtain the new points by the formula 31. Here, the eta are the independent standard normal distributed variables, and that's why the points x sub g are distributed in accordance with normal law, with the center in minimal point of the generation and the covariance matrix C, given by formula 32. There is no necessity to calculate this matrix because the formula 31 provides the distribution of the points with accordance to normal law. After that, we find the minimal point of the generation and check the achievement of the accuracy demanded. And go to the next iteration if it is necessary. The test example illustrates this method efficiency. This is the Rabin objective function graph, and the problem is to find maximum. The algorithm under study achieves maximum by 3 generations. It must be taken into account that this algorithm provides the evolution of covariance matrix. And more often, the individuals appear in the vicinity of the best population found at the previous generation. And we can see at this graph that the trial points are mostly inside the scattering ellipsoid. And 3 ellipsoids are constructed, and the blue point is the point of maximum. Only 3 iterations. Now we go to our problem, and we can see the parameters of our accelerator at this slide. And this slide presents the numerical results obtained after optimization. Our problem is multidimensional, multi-extremal problem. There are many closely placed extrema of our objective function. And so we have a rather large volume of generation and a rather large volume of the best points. It took 6 generations to obtain the required accuracy. And in the table 2, you can see the characteristics of the beam at the output of the device. You can see that the phase spread and energy spread are reduced after optimization, and the energy of particles is in the demanded interval, and the number of particles within the separatrix is increased. So the optimization is successful. At this graph, you can see the functions with the functions which figurate in the right-hand part of dynamics equations, and they have the control parameters, and these parameters are the optimization parameters. The dimension of the vector of optimization parameters is 84. At this graph, you can see the functions alpha and phi before optimization and after optimization. Before optimization, the dotted line. Here, there are the trajectories of the particles. You can see the evolution of phase of particles along the structure before and after the optimization. And the evolution of energy of particles before and after the optimization. At this graph, you can see the particle distribution at the plane phase energy, and this curve is the separatrix. And we can see that the most particles are inside the separatrix, and the bunching quality is high. So the most points of our report are as follows. We can demonstrate the beam dynamics model, optimization problem statement, mathematical optimization model. We applied the genetic stochastic algorithm with covariance matrix adaptation, and the optimization results are presented. The optimization is successful, and this indicates the convenience and efficiency of the optimization method. The authors are grateful to Professor Yermakov and Ovsyannikov, Professor Ovsyannikov, for attention to the work and valuable advice. Thank you for your attention.
Thank you. Any questions, please?
A beam is characterized by charge particle density. How did you count the charge particles density in your model?
Thank you. This beam has a rather small initial energy. That's why the account of Coulomb forces is neglected. The Coulomb forces may be neglected.
Weak beam of low intensity without interaction also have some density.
This our model doesn't take into account the density because we do not take into account the Coulomb forces.
No. I think that beam of heavy intensity and beam of low intensity, in both cases we use charge particle density in the functional, and beam is in fact it's described by charge particle density, and we study evolution and then optimize to minimize some functional. And maybe your work is devoted to investigation, the optimization of trajectories when beam.
Yes, I can say that the low initial energy gives the possibility to have not the spread of energy at the beginning of structure, but we suppose all the particles have the initial energy 80 keV, and it isn't the goal of our investigation now to use the density. It is we shall do it in future research. We plan to do it in future research.
Thank you. And how to compare efficiency of this method with another methods of optimization? For example, gradient method.
Thank you very much. We think that it is necessary to combine the gradient method and the stochastic method. It is very important. but the comparison was done not with gradient method, but with another method of stochastic optimization, swarm optimization. This slide contains the information, and one iteration processing using the method under study is 2 times faster than one iteration processing for swarm optimization.
Thank you.
Thank you. Any other questions, please? No? So, thank you, Ирина Дионисовна. Пожалуйста, уберите демонстрацию экрана, чтобы следующий участник мог. Our next presentation is factor values measurement and heteroscedasticity by the example of field electron emission signal identification. The speaker is Andrei Yurievich Antonov. Please.
Good afternoon, colleagues. Do you see me? Do you hear me?
We can see you.
Okay.
And here.
Here's my presentation. Here's full screen mode. Is it okay?
Yes, yes, yes.
Okay. Among the methods for non-destructive investigation of a substance, emission ones can be distinguished. If a strong electric field is applied between the cathode and the anode, then the field electronic emission phenomenon is observed. Field cathodes have many advantages, for example, lack of inertia and high current density. These properties give us an almost perfect control system. The main studied characteristics of the phenomenon are emission images, energy distributions of electrons, and current voltage curves. We pay attention to these characteristics. This slide shows emission images of tungsten taken with the Muller electron microscope. They correspond to the current density distribution over the cathode surface. Dark spots here are associated with high work function values. This slide shows the energy distributions. They also, as previous figure, differential characteristics. They can be complicated for non-trivial materials. Here, for example, bimodal distribution. Current voltage curves are integral characteristics. They investigated in first step for investigator to construct the current voltage dependence. Their slopes dependent on work function of materials. In selected coordinate system, field electron emission theory was proposed by Fowler and Nordheim. The relationship between voltage and current is valid in both differential and integral cases. Here we can see current density J and electrical field strength E. Here total current, total emission current and voltage V. A and B in both cases are constants for selected for chosen emission system. The dependence of current on voltage can be represented as Formula 3 in dimensionless form. This transformation 4, known as Fowler-Naggame coordinates, we can obtain linearized responses 5. Here y is response, x is factor. X corresponds to the voltage, y corresponds to the current in new coordinate system. This is a simple regression model. Let us write the current response of the emission system that's shown here with voltage errors and current errors. Let errors be normal random variables with constant signal-to-noise ratio. In terms of regression analysis, we investigate both regression model and errors at the same times. Then it is easy to show that current errors lead us to the deviations in responses with an approximately constant variances for each factor value. Constant standard deviation. This is a situation of homoscedasticity. Voltage errors lead us to deviations in responses with progressive variances for each factor value. Progressive due to this term in Formula 7. This is situation of heteroscedasticity. Thus, there are two limit cases for us. Delta sub V equals 0 and delta sub E equal 0. We fixed A and B values to get some signal in selected voltage range here. When passing the Fowler-Nagame coordinates, we assume that values of factor are measured exactly here. Factor X without wave instead of Y or Y. This is a starting point for regression analysis. On slide, we can see the figure voltage errors can make a more significant contribution to the error. Instead of current errors. This figure shows the process of generating errors introduced by voltage deviations. First, the factor with error is replaced with the exact value. First step. And secondly, the observed value is also interpreted in a different way. I listed two slides. Start where factor with error replaced by factor without error. We think that we measure it precisely. Least squares method without any additional analysis is the main feature in field emission research area. No significance, no confident intervals, no check for normality of residuals, and so on. Simple formulas presented here, and here we can determine the residuals of the regression model. Instead of deviations presented here, this deviation of measured responses and predicted values y this hat based on obtained estimation. We will run most tests of on 5% confidence level. The test for significance is the simplest since the studied model is embedded in the signal. So procedure is described here. One of the most implemented characteristic is the squared sum of residuals. Second test is normality test. Normality hypothesis was checked with powerful Shapiro-Wilk test. All statistical tables can be found in most sources, common sources about statistics or mathematical statistics. We can rely on paper of Shapiro and Wilk also. The Darwin-Watson test is used to test after correlation. This one test is test for independence of residuals. Here we calculate statistic D, and there are some conditions with when we can make suggestion about our hypothesis. And finally, we consider the situation with homoscedasticity. For single measurements, there is an interesting method, Goldfield-Quant test. The test procedure as follows. The domain of the factor is divided into 3 subregions. The central part should contain about a quarter of all the points, and it is taken out of consideration. In the remaining subregions, the number of measurements must be the same. This slide shows the situation with current errors. Delta sub V equals 0. 10 measurements, approximately quarter is 2 points, and 4 points in every subregion. Blue dots are modeled responses, and gray dots are phantom data. They need to show situation with homoscedasticity, and gray line is predicted response on wall domain, red and magenta lines in subdomains. The slopes in the subdomains are approximately equal, so the residuals are homoscedastic. Second situation with voltage errors, delta sub I equals 0. Here, phantom data demonstrates as heteroscedastic situation. All notation preserved. However, a single data sample may be arbitrary varying. This fact is referred in this figure. And also, small deviations at small values of the factor, are observed in all data samples. The statistical conclusions are different. Blue dots correspond to the sample which there were no complaints, no autocorrelation, no heteroscedasticity. Orange triangles show autocorrelation revealed by Darwin-Watson test. Green triangles demonstrate heteroscedasticity.
I'm sorry, how much time do we need?
I almost finished.
Да, почти заканчивают.
Понятно. Finally, brown rooms are recognized as both autocorrelated and heteroscedastic at the same time. We consider the problem of parameter identification of the field electron emission signal. Attention is paid to the case when the values of voltage can be measured inaccurately. Thank you for your attention.
Thank you.
Okay, thank you. Any questions, please? No questions? Okay, thank you, Andrei. So it was our last presentation, and our session is over. Может быть, председатель как-то подытожит?
We have very interesting reports in the previous section, in this section, and I think that level is high, and I thank all participants and moderator especially. Thank you. And we meet at closure. Yes?
Yes. Yes.
In
Thank
half
you.
an hour, in 2 o'clock, the closing ceremony.
What? How many?
В 2 часа будет церемония закрытия.
Okay. Thank you very much.
Мы тогда закончили.
The session is over.
Is over. Я бы хотел, поблагодарить Анну Геннадьевну за блестящую организацию конференции, за огромный труд, который был проделан. Спасибо вам большое.
Спасибо.
Вот. Ну, тогда что хотите сказать, Аня, нет? В завершении.
I think Professor Животин already has said everything. I just can additionally thank all the participants for today's presentations and their contribution to the success of the conference. Without it, it wouldn't be happen. So I can just say that see you in half an hour. We will make conclusions and present some statistics. Unfortunately, I won't be able to attend it, but I gave all the information to Professor Petrosyan and Smirnov, the chairs of the conferences. So they will inform you about everything. Yeah.
Okay, thank you.
Yes, thank you. And also I invite everybody, I don't know if you get my email from yesterday. that after the closing ceremony, we organize a special round table dedicated to our Faculty of Applied Mathematics and some problems and questions and our achievements in the field of education, science, and the way how we should move forward. So I invite everybody, and drinks and eats welcome. But you should take it your own with you.
Anna
We will
Gennadievna, so
cheer everybody.
Anna Gennadievna, thank you very much for your attention to participant.
Thank you.
Thank you. Anna Gennadievna, I also thank you very, very much. A great deal.
Thank you. It's a pleasure. Okay, I think we can stop.
Yes.
Я завершаю трансляцию тогда.
Ага.
Да? Все, всем спасибо. До свидания.
Таня.